Good evening, friends. How is everyone doing today? So, looks like not a lot of people are joining in, or maybe they're joining in late. That always happens. Anyways, so yesterday we had looked at ML Primer. Now, ML Primer is where we understand what do you call it? Where we understand different machine learning algorithms that we will come across. All right. So now we'll take a look at the various steps we can perform for analyzing our e-commerce sales. All right. So that would be a target. Okay. So today we'll cover something we call pre-processing as well as EDA. So first we have to understand what is the purpose. The purpose is simple. Why do we need to do EDA? We need to do EDA because EDA will give us understanding of the data. Okay. And EDA will allow us to fully grasp what is going on, what we are doing within that data. Okay. So that's why we need to perform EDA, and we perform pre-processing to clean up the data. Now the data is not always going to be clean. You have to remember that the data is it's going to be not easy to read if you don't clean it up. Okay, so this is where EDA and pre-processing come in. Okay, so that is what we'll be aiming for today. That would be our aim for today's class. So EDA and pre-processing, let's try to understand. Now, these two go hand in hand, and we'll see how. In EDA, we try to visualize our data. Visualization help us understand how the data is behaving, what is within that data. Okay. And then in pre-processing, we are cleaning up the data. All right. So we'll try to cover up a few major concepts involved in EDA and pre-processing. We are not going to spend too much time on the boring theoretical details. We'll spend a few minutes and then we'll code alongside. Okay, so we will be doing the coding work alongside. But first, let's try to understand the important parts. Important parts for pre-processing. So we have a few steps we can perform. One of those steps is what we call typecasting. Now, typecasting is changing the data type.
Changing one data type.
Changing the data type. Now, if we have an integer value, you might want to change it to float values. Int values would be, let's say you have x equals to 8. This would be an int value. You want it to be in a float. So you can say x, when it becomes 8.0, you change it to a float. So that is typecasting. Simply you're taking the data and you're converting the format. All right. And then you have duplicates. Okay. Duplicates is basically repeated values. So if you have duplicates, same output is being repeated multiple times, and that is not giving you anything new. Okay, that is not adding anything to your model. If anything, it is probably skewing your data towards a bias. It is giving some bias to your data. So let's say, for example, one night you were up late, just double checking all your orders, and you had a customer. All right, he had ordered 10 items, and he had address you had here, you had previous sales, etc. All these details were there. You dozed off, and you control V this information 10 times. All right. And then you woke up and carried on from the next entry without realizing that 10 times you had repeated the same entry. Now, if you try to use that data for this purpose, you'll end up in a scenario where this user's information has been repeated way too many times. If you just had 100 entries and 10 of those entries are in one person's name and they are repeated, it's going to affect the model. So that's where we want to avoid having duplicates, because duplicates are not adding any new information. They're just adding noise to our data. Okay, so that is duplicate. All right, so then we have outliers. Outliers are anomalies in the data. Now, let's say you have around 500 clients who are constantly ordering things from you, and their order price varies from 500 to 200 plus shipping, whatever the standard shipping is, 40, 50, 60, depending on their area. And then suddenly you have this one client who comes in, who orders 10,000 worth of stuff, and he's saying, I will pay you 5,000 extra, ship this to Canada. Okay, he said, whatever custom charges it will take, I will take care of that. You just send that stuff to Canada. So all of the sudden, where your average sale was, let's say, for example, 100 for these 500 clients. So you had 500 entries and your average was 100. So what? 50,000 by 500 is going to give you 100. Okay. So you had sales of 50,000. All of the sudden, your sales are 65,000 from 501. This will push your average around 130. All of the sudden, you're seeing an increase, and it's not because your sales have suddenly increased. It's because that one person has decided that he wants to spend too much money. He wants to spend too much money. So when he wants to spend too much money, and you're more than happy to oblige, you're not going to say no to a 50. You're not going to say no to a 60,000. Sorry, a 15,000 order, right? You're not going to say no to it. So just 1 minute, guys. So you're not going to say no to such a big order. Okay. Instead, you will say, okay, fine, I'll ship it and I'll do it. But when you're analyzing, does this data add anything that you would normally expect? Now, this is probably a once in a year situation, or once in your entire business cycle, where you have a client who's willing to pay 15, 20,000 for a single order, when your average order value is about 100. Okay. So this scenario here is what we call outliers. Sorry, guys, I'm just really sick. So when you have outliers, they're affecting your model. Now your model will think that, oh, her average sale is 130. Okay, so your average has increased by 30. And if you have another 500 orders, an average increase of 15,000 from your expected value is what it is predicting. This is prediction, by the way. This is prediction, just an example. Okay. So it is predicting 15,000 more than your other sum. So if your sales were 50,000, they went up to 16,000. Now, ideally, you were expecting the sale to go up to 1 lakh, but this is saying 1 lakh 15,000. Okay. So when you have a situation like this, your model performance will be affected. So that is what we call outliers. Okay. So you don't want outliers. You want to make sure that outliers are treated. So to treat outliers, we can either remove them completely. We can just do something we call trimming, or we can bring them within the IQR range. Okay. So we'll see how we can do that. All right. And then we have missing values. Now, missing values are simple as the name suggests. Missing values. This is different from duplicated values. In missing values, you have some information that is missing. Okay. So we either try to um, we either try to replace the missing values. Missing values within Python are shown as NaN values. Okay, so we either try to replace it, or we drop it. So one option would be drop. You drop the missing values altogether. Okay, so when you drop it, you're losing some record. Or you can do something we call imputation. Okay, so imputation, we have three kinds. We have mean, average imputation, median, taking the middlemost value, and then we have mode. Mode we use for categorical data, that is non-numeric data. Okay, so this is something we have to keep in mind. So in mean and median, we can do it for numeric data, and mode we do for categorical or non-numeric data. So this is missing value treatment. All right. Just 1 minute. Okay. And then we have, let's just start fresh, different color. And then we have dummy variables. Dummy variables. Now we had seen yesterday that machine learning algorithms, most of them prefer numeric values. So if you are predicting customer churn, right? Are they going to order again? Yes. They're not going to order again. They're not going to order again. Yes. So either you can apply classification on this, or if you want to apply regression or any such models, you have to do dummy variable creation. So what dummy variable creation does is it will create dummy variables for this. This will become 0. This will become 1, 1, 0. So like this, it will replace the entire categorical data with numeric values. Okay. So in this, we have two types. We have one hot encoding. In one hot encoding, all the values are replaced by zeros and ones. That's it. Zeros and ones. So if you have yes, no, maybe. Okay, maybe like that you have. and then you have yes and no. Okay, so what's going to happen here is it will create three columns. First, it will create a column for yes. It will say 1 0 0 1 0 0 1 0. Then it will create a column for no, 0 1 1 0 0 0 0 1. Then it will create a column for maybe, 0 0 0 0 1 1 0 0, like that. But again, you're having repeated information. These three columns are essentially representing the same information again and again. So that's what we want to avoid. So for that, we have something called label encoding. Okay. So in label encoding, the values are replaced by numeric values, but it can range from 0 to n. N means how many unique values are there. So what will happen here? It will first see yes. It will replace yes with 0. Then it will say no. It will replace no with 1, 1, 0, 2, 2, 1, 0, like that. So if you had another column called don't know, this will be given 3. Like that, label encoding works. So in certain situations, label encoding is more useful. And in certain situations, one-hot encoding is more useful. We just have to make the judgment based on our own understanding of the data. Okay. And then another thing we do is we standardize. Or normalize the data. Now, what we are trying to do here is we are trying to reduce the range of the data. Range reduction is what we are working on. Okay. Now, why we want to reduce the range? Because the more range, more chances of inaccuracy. More chances of increased computational time. It might take it longer for it to compute when the range is higher. Okay. And then the same time, it might take it, what do you call it? Yeah, inaccuracy and computational time is the main reason why we do it. So we want, let's say we have a range. We are having something called total sales. So the lowest value for total sale is 50. The highest value is 50,000. The range is very high, from 50 to 50,000. So in that context, we want to reduce it. So we can do standardization or normalization. Okay, we can apply either of them, and it will reduce the numbers to a very small scale. You might see this 50 to 50,000 being reduced to a 0 to 1 scale. Between 0 to 1, those values would be there. Okay, so you might see 50 as 0.001 and 50,000 as 1, something like that. All of the sudden, the range is less and the model is performing better. Okay, that's just how computers work. Really, that's just how algorithms work. You want your range to be small. Now the range is 0.999 something instead of 49,950. Okay, that makes a lot of difference. So that's where we do standardization. Okay, there are a few other ways to do it, but we'll not focus on that. We'll just focus on these main points, because again, like I said, I don't want to bore you guys into sleeping. Okay, and then we have EDA. EDA helps us understand the data. Okay, understand the data. Now, Let's say you have a friend and your friend is going through a tough time. He comes to you and he says that, hey man, things are not going well for me. I'm feeling stressed out. How would you just happen to know what's going on with him? You would ask him, right? You would ask him to explain it. You would ask him to explain his feelings, right? He would talk to you and you would try to understand. Okay. Without asking, you would not know what exactly is going on in his head. So, similarly, in EDA, we are taking our data and we are trying to see what that data is telling us, what that data is depicting to us. So, we take a few business moment decisions. The first business moment decision is what we call central tendency. We're trying to find the centrality of our data set. So for central tendency, we take mean, median, and mode. Okay. And then we take the second moment business decision, which is the dispersion of the data. And here we are taking variance and standard deviation. So these are the first two business moment decisions. Okay, so we are trying to figure out how our data is centered and how far is it spreading. Then we have the third business moment decision, which is what we call skewness. Skewness tells us how the spread is happening, how the data is spread. Okay, it is focused on the distribution of the data. Okay, so let's say we have some data. It looks something like this. You have these peaks here, and then it slowly, gradually tumbles away down like this, continues on for a long time. So here, most of the data is concentrated here, but we just have some data points that exist away from here, these points. Okay. So when the data is concentrated on the left, when data is concentrated on the left, we say it is positive skewness because this tail, so this data would look something like this. This data would look something like this. This tail is trending in the positive direction. Okay. And if it was the opposite, then we would have negative skewness. Okay. So that is skewness. And then we have the final business moment decision, which is kurtosis. Again, we are taking a look at negative and positive. So we have kurtosis. That is the fourth moment business decision. Again, this has something to do with the distribution, but in kurtosis, we are checking how the data is tailing. So for example, we have this data. Okay. So we have some data points and 1 second. So we have some data points and it is looking like this. You have a lot of high value data away from the central points. Okay, a lot of high volume data away from the central points, and then you have some smaller points here. So this data has a wider peak. Okay, this data has a wider peak. When the data has a wider peak, we call this negative kurtosis. Okay. And when the data has thinner peak, we call it positive kurtosis. So these are the 4 business moment decisions you might come across while you're working, while you're doing EDA. Okay. So, and then we have graphical representation. We'll not spend too much time on the theory here. We'll simply just understand what graphical representation is, and we'll move forward. Graphical representation means representing the data in a graph. So we have univariate, bivariate, as well as multivariate examples. Okay, so these are the 3 different types of data you might come across when you're working on graphical representation. Okay, so univariate basically means a single variant. It just, what does it mean? That you have only one variable and you're using it. Okay, and then bivariate means 2. Okay, bi means 2. Always remember, bi means 2, uni means 1, and tri means 3. Okay, so that is some basic knowledge you need to have. Okay, and multivariate means you're taking more than 2 variables. That's it. You're not doing anything else. You're just taking more than 2 variables. Okay, so that is bivariate. So now we'll quickly switch over to our code. Now I know everybody is probably already bored by what we have done so far. They're saying that let's just get some practical done. So now we'll quickly switch over to our codes and we'll start working on it. Okay. So just give me a minute. Let me just open up my Jupyter notebook. Anaconda is loading up. So until then, if you guys have anything you want to share or anything you want to ask, you may use this time. No question. Yeah? All right, not an issue. So just give me a second and then we'll get everything started. Okay. Okay. So let me just zoom in a little so everybody can properly read. So we'll be going through EDA today, and tomorrow we'll start with algorithms. So first, we have NumPy. What is the use of NumPy? This is used for numeric calculation as well as to deal with arrays. Now, a lot of the work in Python comes down to using arrays or series. So we need to know NumPy. Panda is used for data frames. Panda is used for data frames. All right. So pandas is used for data frames as well as series. So you might come across some series as well. So we do that. Now matplotlib.pyplot is for plotting. And we use it for 2D plotting. And Seaborn we use for 3D plotting. Okay, so these first four libraries are there. And then we have sklearn. sklearn is short for scikit-learn. All right, sklearn deals with scientific calculation. That was the original purpose. Okay, it was designed on top of NumPy, and it was designed to deal with scientific calculations. Okay, but we use it for other stuff now, like we use it for its modules. What sort of modules we use it for? We'll see. Okay, so first we import all these libraries. So we'll just let it done. We'll call our CSV file and we'll take a look at the CSV file. So this is our data. We have 1500 records. We have some order ID. We have some amount. We have the profit, quantity, the category, and the subcategory. So you can see the amount is ranging just by a visual look. Amount is ranging from 8 to 2366. Similarly, profit is ranging from negative 1148 to 552. Okay, so there is a lot of variance within this data set itself. Okay, data set will go through it. I'll ask if I can share these data sets. Okay, so first we find the duplicate values. So we use this df.duplicated command. It will return true false values. Wherever it is saying true, that means there are duplicates. Wherever it is saying false, there are no duplicates. So we have 0 duplicates. So we don't have to worry about this in this data set. You might see these duplicates somewhere else, but we don't have to worry about them here. Okay. And then missing values. Any NA values? No NA values. Okay. Great data set. We don't have to worry about all those things. All right. So moving forward, we take a look at data types. So we have different data types here. Object. Object means string. It can be string. Okay, it doesn't have to be string. It can be string. Float and int. Float is decimal values and int 64 is whole numbers. Okay. So we can see the data type. Now we'll just quickly use this info command here instead of having it on the same line. So we'll do df.describe. It will give us the mean, the standard deviation, the min max, the percentile values. What are the percentile values for all the numeric columns? Okay. So now look at the range for amount. Look at the range for profit. Okay. The range is huge. You got 5029 minus 45. That is 5684. That is a massive range. similar to this. This is almost 3,700. Okay. So this is something we'll have to deal with. Okay. And we'll deal with it based on the algorithm we are using. And then we are taking a look at df.info. So first it is going to give us class. It's a pandas data frame. It's going to tell us how many non-null objects are there within each of those columns. What type of data is there? So all these things that we have checked here, we can check using this df.info. So this can be a very useful command when you are doing pre-processing. Okay. And finally, it is going to tell us how much memory that data frame is taking. Okay. How much memory that data frame is consuming. Okay. So we do that. And then what I'm trying to do here is I'm trying to separate out the numeric columns. Okay. So we have amount, profit, and quantity. So I'll take them as separate and we'll just quickly take a look at it. So now we have these numeric columns, profit, amount, and quantity. Okay. So here we have written a simple for loop. Now, anybody wants to take a guess what this for loop will do? I mean, the code is in front of you. So why have I written a loop here instead of just writing the code? Anybody wants to take a guess? It is for outliers. Yes, exactly. It is for outliers. But why am I taking a loop? Why am I writing a loop? Why can't I just check individually? Why do I want to do all these steps? I want to do all these steps because I want to avoid repetition. I don't want to write box plot, column name, all of those things again and again. So instead, I create a new data frame, store all the numeric values, and create a for loop. So within this for loop, I'm doing for column in numeric calls, this data frame, I'm saying plt.figure. So what it will do is after each column, it will create an empty figure for that box plot to be plotted on. If you don't do this, you run into some issues. So if I remove this and I run this, you see, can you make any sense of it? It is saying that there are outliers, but that outlier is right is within that within the whisker box. No, because it has created only one figure, and in that figure it has plotted three separate graphs. So we have to create an empty figure every time we want to do a loop like this. So if I run this now, you can ignore the warning as long as it is not throwing any error. You can just ignore this warning. So now we have amount, we have profit, and we have quantity. Now, my question to you here is, let me just reduce the size a little. So now we have amount and profit. Take a look at these graphs. Would you say that maybe these values might not actually be outliers? These might be actual expected values. I mean, if you take a look at it, you're looking at hundreds of records over here. over here, over there. You're looking at hundreds of records. Now, if you want to do pre-processing, if you want to treat them like outliers, you can. There is no stopping you. You know, you have every right to do whatever you want to do. But I personally wouldn't treat them as outliers because I don't think they are actually outliers. They're just data points that are outside the normal distribution. Okay. But they're still giving us information. Okay. These points may be outliers, these standout points, but still, I'm just going to act like they're not outliers. But here, now this is what I will call outlier. This is something I will definitely call as an outlier because we have a very few data points that exist outside the normal distribution. Okay. So we take the IQR, we find the 75th quantile and the 25th quantile. We define the upper and lower limit. And if you want to see, you can just quickly write lower limit. Now it converted this cell format. Wait. I'll just yeah. Lower limit, comma, upper limit. So lower limit is minus 2.5, upper limit is 0.95. So now here what I'm doing is I am creating a new column called df underscore replaced, and I'm replacing the values that are higher than the upper limit with the upper limit itself. The values that are lower than the lower limit, there are no values by the lower limit itself. And then I'm saying what column to do it on. Okay. Salaries. Where did I say salaries? Okay. So here we have to make sure we are not making any mistakes. Okay, now we do that. And now we'll quickly just write a command. And now again, it has plotted. So now you can see here that the outliers have actually been replaced. Okay, the outliers are now gone. And we have created a new column called df underscore replaced. So again, the same thing was happening here. Now, if I draw this box plot, you can see those box plots are now overlapping. So that is one thing you have to be careful about, especially when using Jupyter Notebook or Google Colab, that you have to make sure everything is in the correct order. Similarly, we can do winsorization. Okay. For that, we use feature engine, but we don't need to do winsorization. We'll only be doing this. So now we have df replaced and quantity. Okay. So quantity is the original and df replaced just the new values, winsorized values. Now we have another data set. This is called list of orders. So this again, similar order ID, but here what we have is we have the order ID, we have the order date, we have the customer name from where they are ordering, the city as well as the state. So here you can already see that there are NaN values. Whenever you have these NaN values, these are null values. That means these records are empty. And we are seeing that we don't even have order ID, order date, name, state, and city. No information is given. Okay. So we check for how many null values we have. 60 in each. That means that accidentally somebody added 60 rows. There was no need for these rows, but somebody decided anyways, we'll add it. Okay. So we'll just simply drop them and 0. Okay. All right. So now here we are dropping it because they're not adding any information to our data set. They're just simply junk information that happens to exist within our data set. So now we are checking the where each customer is from. So we have the city name, how many customers are there from each city. So you can see that Mumbai and Indore dominate. They are both 50 plus. Then we have the distribution that looks something like this. So Pune, Bhopal, Kolkata, Bangalore. Okay. You even have Gangtok, Goa, Kohima, Udaipur. Delhi is there twice, once as a city, once as a UT. So this, because of it showing up as state as well as an UT, it is throwing some error. But anyhow, from this, we can see that a lot of our customers are from Mumbai and Indore. So maybe we are based in Maharashtra itself or in MP itself, and we are, selling our products nearby, because Pune, Ahmedabad, Bhopal, and even Kolkata, all these are centrally, very central, close by, right? So we are selling it. And then we have places like Chennai, that is very far off compared to central India, where you have no values. So this is one way. And then we can also take a look at what all is being ordered. So we have three categories: furniture, clothing, and electronic. So which these three items from clothing are being ordered the most? The quantities are nearly 200 or greater than 200. We can say the quantities are greater than 750. So we have stoles, handkerchiefs, as well as saris. So these three items are being ordered the most, and the least ordering is for tables. People are not ordering as many tables as you might want somebody to be ordering. Okay. So 1 minute. So based on these two visualizations, we can draw some conclusions for ourselves. We can say where are most of our customers from, where is our what products we are selling. Now, if you are a business, would you rather focus on the products you're selling well, or would you start focusing on selling more tables? If I was there, I would probably focus on marketing, not only just the stole, handkerchief, and the saris, but I would also focus maybe on marketing electronics more. Phones, electronic games, printers, accessories, they're already selling at a decent quantity compared to furniture items. Okay. So I would maybe focus on that. So you can make some suggestions. And then we are trying to see collinearity. So there is weak collinearity between the numeric columns. Okay. So that you have to know. Okay. And then we are merging those two data frames, because we'll see why we have merged them tomorrow. But now we are merging it, and we are merging it on the basis of order ID. So if we take a look at our data frame, order ID, for example, T25601, we already have multiple orders for that. So maybe this one customer named Bharat from Gujarat, Ahmedabad, ordered furniture and clothing and electronic items. So he ordered different items. So we are merging it based on that. So we check the shape. We have 11 columns now. Again, we'll quickly just check for NA values, no NA values. Yeah. So this is the data ordered, sorted by profit. How much profit you are making from each customer. Okay. So based on that, maybe we can maybe figure out that, hey, why that customer is earning so much money for us and that other customer is earning so little money. What could be our what could be the reason? Maybe it's the transportation cost. I mean, also you may notice a trend here: furniture, electronics, furniture. You sold items that were nearly 3,000 and you're still making a loss of 2,000. Maybe you need to focus less on furnitures and maybe you need to focus more on electronics. You're making a profit of nearly 1,700 for a sale of 41,000. Profit of nearly 11 here. So you're making almost double profit in some instances. Okay. So maybe you need to focus less on furniture and focus more on electronics. All right. And then we are checking how many unique values we have in each column. We have 500 unique order IDs. We have 307 unique order dates. We have 332 unique order names or 332 unique customers. Our customers are from 19 different states, 24 different cities. We have three categories and we have 17 subcategories. We'll just ignore the numeric values here because numeric values are fine as is. Now, we'll ignore this dropping part. We'll see why. I'll show you guys tomorrow. But okay, we'll do that anyhow because it is excuse. This is now a data frame. Okay. So here what we are doing is we are using the scikit-learn's preprocessing library. And from there, we are taking something called label encoder. Now, if you remember, label encoder encodes the categorical data and it will replace it with numeric values. So we do that. We are replacing the state, the city, the category, as well as the subcategory. So we do this. And now you can see state N 4, 4, 11, 10, 0, 0, 0, 19, 17, 0, 1, 2, 113. So like this, we have created numeric values for each of the unique categorical data. And then finally, we create a normalization function. Okay. So we apply this function. What is the error it is showing here? I think it's the order. Okay. There is category and subcategory. So let's just quickly drop these columns first. Yes. And now let's run this. Now if we run this, cut and this will be F. Yes. So now we'll apply this normalization function and we'll apply it on each of these values. Okay. Now, if you take a look at it, and this is just to show you how we can do it. I'm going to do one thing. I'm going to create this data frame again quickly, and we'll run all these steps again. So we create a data frame, and now we'll drop city, state, category, and subcategory. Okay. So now if we take a look at our data frame, we have amount and profit. Okay. So we'll only do it for amount and profit. So we'll specify the range 0 and 1. Okay. Now look at amount and profit. It was, the range was in the thousands, and now it is between 0, 1. So that way you can normalize your data. Okay. And then we create this data together, and we have this amount, profit, quantity. Quantity and DF replaced are giving the same information. So we can drop quantity. State, city will also drop this amount and profit. Okay, we'll just keep the normalized value. So this is pre-processing. And tomorrow we'll use this pre-processed data and we'll try to build algorithms. Okay. And we'll see how those algorithms work. All right. So we'll wind up today's session here, and I'll see you all guys tomorrow. So tomorrow we'll try to work on k-means clustering. Okay. All right. Thank you, everyone. I'll see you guys tomorrow. Thank you. Thank you, guys.